All right, let's take care of Chapter 9, Lesson 3. This lesson is going to be just about different laws that scientists have figured out about the way that gases behave. All right, so there are a lot of laws about how gases behave, but you have the fortunate position of being in sixth grade, and you only have to know a couple of them. So the first up is just going to be a basic law about gases. If the volume of the container that's holding the gas stays the same, it's a fixed container. The temperature is going to control the pressure of a gas. If the temperature goes up, so will the pressure of the gas. If the temperature goes down, so does the pressure. And pressure, if you remember back to a couple of weeks ago, pressure is the collisions of gas particles against other gas particles and the sides of their container. So, in the basic law of gas, if the temperature goes up, you're going to get more collisions because the particles are going to be moving faster. When the temperature goes down, the particles slow down, and so you get less collisions. And that's going to give us less pressure. So, here we have a couple of different diagrams that are kind of showing the same thing. So, let's look at this diagram over here on the left. At a low temperature, you can see that the direction arrows or direction lines showing the movement of the particles is less than the particles over here. At a higher temperature, these longer lines mean that these particles are moving faster. And if these particles are moving around faster, they're going to bang into each other more, at least more frequently. And they're going to hit the sides of the container more frequently. And that's going to give us higher pressure. Um, and if you look at this diagram over here on the right, they're kind of showing the same thing. The size of the container looks like it's staying the same, but we've got, if we look up here, higher temperature, we've got longer direction lines, and that means that the particles are moving faster. Lower temperature, we have smaller direction lines showing that the particles have slowed down, and they're going to hit each other less, and they're going to hit the sides of their container less. What I also really like about these diagrams is that they do show conservation of mass. Over here on the right, if we count blue particles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Down here, 1, 2, 3, well, there's more than 10. All right, this one doesn't. This one over here, maybe it does. All right, I misspoke. My bad. This diagram does a bad job of showing conservation of mass. And I'm not going to sit and count red ones for you. But if you want to pause the video, you can tell me later if this diagram on the left follows the law of conservation of mass, because the one on the right sure doesn't. All right. The second law that you are going to have is going to be about Charles's law. This was a scientist whose last name was Charles, and he figured this out about gases, and so he gets a gas law named after him. All right. For Charles's law, instead of the container being fixed, we are now going to have a flexible container. And that means that the container of gas can grow and shrink. Charles figured out that the temperature won't change the pressure, but instead the temperature will change the volume of the container. If the temperature increases, the volume of the container increases, but the pressure remains the same. If the if the temperature goes down, the amount of collisions go down, and so the volume of the container shrinks, and that makes the pressure stay the same. We have the same amount of collisions because the container shrunk to match the lowering temperature. So here we have an example of a flexible container, a balloon. Balloons can expand and contract based off of temperature. Now, this one seems to do a much better job of the law of conservation of mass. 1, 2, 3, 4, 5, 6 particles. And over here on the right, 1, 2, 3, 4, 5, 6 particles. Now, if we put the balloon filled with gas into ice water, that's going to lower the temperature, and that's going to lower the speed of the gas particles. And so they're hitting the sides of the container with less energy. And so the balloon is going to shrink. Um, Over here in the boiling water is going to cause the particles to move faster and hit the sides of their container with more energy, causing the balloon to expand. But we have the same amount of collisions in both balloons. Less speed, but less room to move around. More speed, but more room to move around. So it balances out. The pressure is going to be the same in both containers. The amount of collisions is going to be the same in both containers, but the size of the container is what's changing. All right. The third law that we have to know is about a guy named whose last name was Boyle, and he figured out that if the temperature isn't going to change, but the volume of the container can change, that's going to determine what the amount of collisions, pressure. So if the volume of the container increases, but the temperature stays the same, the pressure will decrease because the particles are moving around with the same energy, but now they've got more room to move around. So there's going to be less collisions. Pressure will go down. If the volume decreases, but the temperature stays the same, we're going to have more collisions because the amount of room that the particles have to move around has shrunk. And so we're going to get more collisions, and that's going to give us more pressure. All right. So quick check. 1, 2, 3, 4, 5 particles. 1, 2, 3, 4, 5 particles. This one shows a conservation of mass very, very well. All right. So in this one, the particles have much more room to move around. So that means they're going to hit each other less, and that means the pressure is going to go down. If the volume goes down, well, the particles have the same energy as they did before, but now they have less room to move around. And that means they're going to hit each other more and hit the sides of the container more, and the pressure is actually going to increase. So, with Boyles' law, the temperature stays the same, but the volume is going to control the amount of collisions. More volume, less collisions because there's more space to move around. Smaller volume, more collisions because there's less opportunity to not hit each other. All right. So you're going to see on the quiz diagrams that look like this. If you really, really feel like it, you can pause the video and count the particles and let me know if this follows the conservation of mass. But we'll assume it does. We have one, looks like weight, that is pushing down on the lid. And so the particles have more room to move around, so there's not a whole lot of collisions. If I add a second weight, the volume of the container decreases because now there's more weight pushing the lid down, and that's going to give these particles less room to move around. They're going to hit each other more, and that's going to increase the pressure. If I add even more weights, that's going to push the lid down even further. Now we've got the even more collisions because there's less room to move around, and that's going to cause my pressure to go up. So your quiz this week is going to be a lot of showing diagrams, and you had to figure out whether it's Charles's law or Boyles's law. Mr. Bogdan's official advice is look on the graph for some sort of indication on temperature. Charles's law involves temperature, Boyles's law does not. So in this diagram, we have the same amount of weights, and right there it says temperature is increased. When the temperature is increased, the volume goes up, and so we have the same amount of collisions, and so pressure doesn't change. Over here, if I cut off Boyles's law, if I crop that out, you'll notice that there's no indication anywhere on this diagram that temperature is changing. And so you have to assume that the temperature stays the same. We also have more weights changing the volume, and that's going to cause more collisions. So temperature, Charles's law, no temperature change, Boyles's law. Couple other hints for the quiz. These are thermometers, and these are pressure gauges. So over here, we see no change in temperature, but pressure is changing, and the volume of the container is changing. Because temperature is staying the same, we know that this must be Boyles' law. Over here, we see a change in thermometers, and so that means the temperature is changing. When you see the temperature changing, you need to think Charles's law. So to further prove that this is Charles's law, pressure stays the same, but the volume of the container is changing because the temperature is changing. We have the same amount of collisions in both containers. As for fun, we're going to show you a second video. It's just for fun. You don't. It's not. None of the 5 questions are going to be about this, but this is just something that can happen with Charles's law. These are railroad containers, and they're often filled with gas. This right there is a pressure regulator. Trains have to have these pressure regulators because if the if the temperature changes too quickly, if it's really hot outside, but then it suddenly rains, that can really cool down the gas inside too quickly. And if you don't have the pressure regulator, the volume of the container is going to want to change. So in this video, they'll show you what happens if the pressure regulator fails and Charles's law takes over. All right. You're going to read pages 316 to 321, answer all the questions, and remember the answer is somewhere in the text. Find that text.